The broadcast is now starting. All attendees are in listen-only mode.
Hello and good afternoon, everyone. My name is Anna Zylik and I am with ICF. We are the vendor working on behalf of the sponsors of Energize Connecticut to bring these passive house trainings to all of you. So thanks for joining us today. We will be recording this training and we'll make this available afterwards. These trainings are at no cost thanks to the sponsors of Energize Connecticut and are part of a partnership with Connecticut Passive House. A reminder that as part of this training and workforce development initiative, we are offering a 50% cost reimbursement for individuals pursuing either FIAS or FEE professional accreditation. So this includes the cost of the trainings and the exam, and once you become certified, we'll work with you to process the 50% cost reimbursement. So if you have any questions about that process, please don't hesitate to contact us. And with that, I'll pass it over to Keegan, who's also with ICF, to talk about the Passive House building incentives.
Yeah, thanks, Anna, and hello, everyone. We're excited to have you with us today. Adam, if you want to go to the next slide. So in addition to the no-cost educational webinar series that everyone is here for today and the professional accreditation reimbursements, the sponsors of Energize Connecticut are proud to also offer robust incentives for builders and developers who choose to pursue Passive House certification in multifamily residential new construction projects with 5 or more units. Next slide, Adam. The Passive House incentive design for the Energize Connecticut program is shown here on the slide. It includes incentives for pre-construction phase for things like feasibility studies and energy modeling, and post-construction incentives for full Passive House certification. The goal is for everyone involved in multifamily construction in the state of Connecticut to be aware of these incentives. So for anyone interested in learning more, please visit our website or contact us directly at the information on the slide so we can discuss this further with you. With that, I will turn it over to today's presenter, Adam Romano. Adam, take it away.
Great, thank you very much. So good afternoon, everyone. We're going to jump into the presentation today talking about reasons for switching to all electric. But before we do that, let me just introduce myself and then we'll talk a little bit about the webinar. So I work for Stephen Winter Associates. We are a firm that provides research, consulting, and advisory services to help improve the built environment. And we do that through energy conservation and management, sustainability consulting, green building certification, and accessibility consulting. My name again is Adam Romano. I am a principal building systems consultant with Stephen Winter Associates. I've been with the firm for about 3.5 years, but I've been in the energy and engineering efficiency space for going on 18 years, and started to work on Passive House projects back in 2012. Worked on about a dozen of those projects so far, from single-family homes to multifamily buildings. I spend a lot of my time now looking at electric-based systems and applications for buildings, all over the country. My contact information is up here on the screen. If you have any questions after the webinar, definitely feel free to reach out. The learning objectives for today, so we're going to talk about a few different things. So we're going to start with some background, and we want to sort of summarize the benefits of electrification. Then we'll jump into discussing the major barriers and major considerations when electrifying residential homes. We'll talk about how heat pump systems work. So we'll, sort of explore the different types that are available and some of the things to pay attention to when you're looking to implement those systems. We'll talk a little bit about the various, equipment that's available now for non-fossil fuel water heating. So there's a couple of different types of water heating devices that we can use that are electric based. So we'll jump into those. And then we will talk about sort of the balance of the fossil fuel-based systems in our buildings. So we'll talk about how we electrify other end uses, such as cooking or clothes drying. So with that, let's jump in. And as you all sort of are aware, there has been a growing interest and a good deal of conversation about electrification and how do we do that, and how do we electrify buildings, and what options are available. And so everyone is really kind of talking about this now as cities and states and start to look at ways to reduce carbon emissions. It's looks that with a clean grid, clean electric grid, we can get to our goals of carbon reduction by utilizing efficient electric-based equipment. But there's other benefits, besides, carbon reduction. There's obviously, health benefits as well. When you combust a fossil fuel, there is a lot of byproducts that are created through that combustion process. And, when you have cities and areas that are, highly congested, that are in urban settings, a lot of the, those byproducts, go into the outdoor air through, your flue piping, and, that impacts the outdoor air quality, which, obviously is going to impact indoor air quality as well. So there's, opportunities to reduce, these issues and reduce, the amount of pollutants that are being generated locally, and we can improve local air quality, improve, indoor air quality, and that can have a great sort of benefits when it comes to reducing, respiratory illnesses or triggers for respiratory illnesses. So there's a good deal of health benefits associated with electric-based systems. Also, the reduced risk of carbon monoxide exposure, right? You see that happens, a lot of times, across the year where, fossil fuel-based equipment possibly is not drafting correctly, and you have the, the possibility of allowing those byproducts to either spill or to leak into the home, and that can cause issues. So obviously, there's health benefits to this. There's also comfort benefits. I mean, when you look at a lot of the options for our electric-based HVAC systems, a lot of them, and we'll get into this, are distributed, meaning that there's not, we don't have to have a central system all the time, and we can have more of a distributed system where there's a localized delivery of heating and cooling, and that can play a big part in improving comfort. Right, so you have the ability to have different temperatures in different parts of the building or different parts of the home, have more control over that comfort. Improve the distribution efficiency by providing the comfort or the conditioned air locally. So there's some comfort benefits that are can be realized as well. And then, there are, cost savings. We do get this question a lot, what do the economics look like? And, that's highly dependent on the price for fuel, right? And the differential between the cost for fuel versus the cost for electricity, and obviously the efficiency of the equipment. But in areas where there's, a high, sort of percentage of delivered fuels, then, the economics do really work out in most cases. So that's something that, you'd have to look into, on a case-by-case basis, and an area-by-area basis, but as the differential starts to get smaller, the case for electrifying can make sense from a cost basis as well. And then obviously the carbon benefits, right? So, with an improved electrical grid, improved generation of electricity and distribution of electricity, tapping into that clean electricity is going to be an important part of reducing carbon, and we want to do it in a thoughtful way. So that's why we're going to get into this, and we're going to talk about how do we begin, how do we do this sort of thoughtfully, how do we electrify buildings in a sort of systematic way, right? So we came up with this this pathway to ditching the gas meter, right? So it starts with making a home heat pump ready. So we'll talk about some of the things that we like to do to ensure that the home is as efficient as possible. Then we'll jump into space conditioning, water heating, cooking and clothes drying, and then some additional considerations at the end. So talking about, a heat pump ready home. So what is a heat pump ready home? It's, it's a home that is efficient. So all of you that are working in the passive house world, you understand the importance of insulation and air sling. You understand the importance of minimizing thermal bridges. You understand the importance or the fact that, space heating, the load on a system is closely tied to the energy efficiency of the home. So this is a great sort of, marriage here while, making sure that, we go ahead and build these homes and build these buildings in the most efficient way possible. That'll help reduce the first cost in terms of, installing a system, the long-term operational cost, and as well, as the comfort. And there's a lot of things that kind of hinge on this. And you kind of only really get one or two shots in the history of a building or a home to really make this work. So the idea is to really make sure that air sealing and insulation are done in a thoughtful way. Right, so air sealing is something that we typically do first, right? So we want to make sure that we're using a good and effective air barrier, and really, as all of you know, it's the continuity, right? So it's the continuity of the materials that are used to provide this this effective air sealing, right? So we want to make sure that we have continuity between different air sealing materials, whether they're rigid, whether membranes, whether it's caulking or other products, whatever we're using to make that air seal. It's really the crux of it is really making sure there's continuity across those materials, and that you're doing a blower door test, and that you're making sure that the blower door guided air sealing is working, so you get some verified results. The same thing with insulation, right? So you want to make sure that the insulation is correct. It's the right amount of insulation for our climate zone. It's again, there's continuity of those materials that we're minimizing thermal bridging. We're making sure that we have continuity of the material that we're using for insulation. And by doing these two things, and making sure that these buildings are designed in a thoughtful way, again, it's really going to have large impacts on the overall efficiency of our systems. So once that is done, right, and we've gone through that process and we've thought about that, next we want to get into, okay, what are the options? What do we have available for us to go ahead and provide space conditioning in an electric way? So first, let's just take a step back and just kind of level set and to make sure everyone has a good understanding of what a heat pump is. And the main difference between a heat pump and other types of, a fossil fuel or fuel-based systems is that, heat pumps don't generate heat, right? So if you look at, a furnace, a gas furnace, right? There's a generation of heat that happens there. So you take in the fuel, you oxidize that fuel, you have useful heat, and then byproducts, go up the chimney, right? So there's, in a sense, there's losses associated with that because you're not going to be able to generate that heat with 100% efficiency. You can come close, but not all the way. Whereas a heat pump, we're moving heat, right? That's the main difference between this. We're utilizing a vapor compression cycle, a refrigeration cycle, and we're utilizing a refrigerant that has the ability to absorb and reject heat at different temperatures, right? So even when it's very, very, very cold outside, the refrigerant that's circulating through the outdoor unit is going to be colder than that outside air. So heat is going to move from hot to cold, causing that refrigerant to boil. Then it's going to go indoors where it's going to reject its heat to the space. And the magic of this vapor compression cycle is such that the efficiencies of these types of systems can be greater than 100%, or usually greater than 100%. So you can have 300-400% efficiency because we're moving heat as opposed to generating it. And that's what makes these a lot different and much more efficient. Now, there are, sort of issues sometimes with older heat pumps, and a lot of people have that, sort of bad experience, let's say, on their mind, right? When they talk about heat pumps. It's what comes up a lot, and some of the barriers that we hear all the time is that they don't work. They don't work in cold climates. And for older heat pumps, that was, relatively true, right? They weren't designed for northern climates. They were designed for sort of lower mid-Atlantic areas where you have, a predominant, cooling load and you need a little bit of heating. So why not make a system that can do both as opposed to building out infrastructure and bringing in fossil fuel-based equipment? So those, worked, well, but once the temperatures dipped below 30 degrees, they became less and less efficient. They weren't able to move as much heat at those lower temperatures. So they relied on, auxiliary heat, which is basically electric resistive. And that drove up cost and lowered efficiency. So there was this bad reputation that still, sort of continues to this day. Newer heat pumps, on the other hand, are, now have been sort of engineered for these northern climates, for these more extreme winters. And they come with, this designation, this cold climate air source heat pump designation. And, there is a organization, the Northeast Energy Efficiency Partnership, which puts together a specification. They send it out to manufacturers. And if the manufacturers can send back engineering data saying that they are showing that they can meet the specification, the criteria, then they get put on this list, this cold climate air source heat pump list. And as you know, a engineer, as a home builder, as a consumer, you can go and look at this list and find equipment that is not only efficient, but also has good long-term operational history, and all the data points are there, right? And I'm going to illustrate quickly what you can see from that list, and they show you all the performance data. So here is an example of a older unit, which would be the unit in gray, so your traditional kind of heat pump from 20 years ago. And then in the orange there is the cold climate air source heat pump. And these both are the same size. So if you look at the nominal rating, how much energy they can move, it's 36,000 BTUs. So they're both rated as 3-ton units when you look at refrigeration nomenclature. And you can see at various outdoor temperatures, 47, 17, 5, we can see the performance data, how much energy they can move, how much BTUs they can give off at those outdoor temperatures. And you see with the gray unit, the older heat pump, right, at 47 degrees, it was at its listed capacity. It was able to deliver that 36,000 BTUs. But when the temperature dipped below that down to 17, well, now we lost a little bit of output. Now we're down to 20,000 BTUs. And then at 5 degrees, we're down to 16,000 BTUs. So there's a drastic drop in the amount of heat they can move at lower ambient temperatures, which again made the case for utilizing more of that auxiliary heat, which brought down overall efficiency. On the orange line, you can see it's totally different, right? So yes, there's going to be a reduction in capacity. Every heat pump that's out there, even a cold climate air source heat pump, is going to have reduction in capacity as the temperature gets colder, because it gets harder and harder and harder to move heat when the ambient temperature drops lower and lower. But what you can see in that line is that, at 47 degrees, the output of that particular unit is up at 42,000 BTUs. So it's actually producing more heat, or moving more heat than its listed capacity. And then as the temperature drops, yes, there's a dip in capacity, but even down to 5 degrees, we're still providing more heat, or moving more heat than our listed capacity, or we're still above 36,000 BTUs. And that's what makes this different, right? Is that they've been engineered to work in this environment and provide you with the heat needed to condition a home. And do it efficiently. You can see that the coefficient of performance, the bars at the bottom, show that there's still good efficiency. They're still over 2. So, it's still 200% efficient at 5 degrees, meaning, if you put 1 kilowatt of electricity in, you're going to get 2 kilowatts out of heat. So there's still good efficiency even at those lower ambient temperatures. Now that we understand, how these systems, work and the benefits of them, let's explore a little bit about the different types that we see out there. And we'll talk about both air source and ground source in this conversation. So let's start a little bit with ground source. So this is commonly referred to as geothermal heating. Here, we have a loop field, and we'll talk a little bit about this, whether that loop field is, is a field, it's a horizontal field, or if it's a vertical well. But the idea is that we are now exchanging heat with the ground as opposed to the outdoor air. And the reason why that is beneficial is that once you get below the frost line and you get down deep enough, the soil temperature stays pretty consistent year round. So you can really highly engineer these systems to work with, let's just call it, 50-degree soil all year round. So, we can dump heat into the ground when it's hot out, like days like today, or we can pull heat from the ground when we're in the middle of winter. But having that relatively stable temperature helps with increasing overall efficiency and performance. Now, the issue with this, though, is you need the space, and there's an added cost now of putting in this loop field or this well. So that's something you have to consider when you're looking at the overall sort of design of the property. Do I have space for this? Can I accommodate that? And can I accommodate the higher first cost for these systems? Once you decide, okay, yes, we're going to move forward with that, you have, a couple of options. The most common option that we see for geothermal is going to be a sort of a central ducted unit. So you're going to have a indoor unit that is inside, which has all of the heat pump components inside of it. So the compressor is there, the refrigerant is circulating through, and then you're connecting that that refrigeration device to that loop, to that exterior loop. Again, whether it's a field or if it's a vertical well. And then here we're going to, again, exchange heat with that fluid. Typically, it's a mixture of glycol that goes out into the loop. And then we're going to then exchange that and condition the space. So you'll have, central ducts that move the air from, the return side to the supply side. And we typically see ranges of, 2 to 5 tons, or 24 to 60,000 BTUs per hour. Good things to pay attention to when you have centrally ducted units is really making sure that the duct design is done correctly. So we want to make sure that contractors are using manual D, that they're going through, that they're sizing the return ducts effectively, they're sizing the supply ducts effectively to make sure we're maintaining velocity and we're maintaining performance, right? Because central systems, tend to, in the past, have, a good deal of issues with delivering on that air to the farther sort of extents of the system. So it's really important to make sure we're paying attention to that good duct design. The same thing is just like a house, just like your building, you want to make sure that the ductwork is air sealed and it's insulated, right? Because we want to make sure that we're retaining all of the conditioned air. We're not losing it as it travels through that ductwork system. So it's going to be important that those ducts are sealed and then insulated, and using the same sort of principles that we would follow with a home. Continuity is going to be important. Not compressing the insulation is going to be important. All of those things that we already do with our buildings. Now, if we decide not to move forward with geothermal, we want to move forward with air source, there's a lot of options there on the air source side as well. So here it's a little bit different. Now we are exchanging the heat energy with the air, the outdoor air. So it's highly variable. Right, so that's the engineering sort of challenge with these types of systems, is that we have this highly variable outdoor air that we have to engineer a refrigeration system that can absorb or reject heat to that air when it's as low as 0 degrees or as high as over 100 degrees, right? So there's a big delta there. There's a big difference. These can consist of an outdoor and an indoor unit, and they're usually connected via a refrigerant line set. So that refrigerant we talked about is going to move from those two components, and it's going to be moving in one or two directions, and it's going to be, again, absorbing or rejecting heat at the indoor or outdoor unit, depending on the mode. Now with air source, we have a couple different options. We have ducted or ductless units. In this case, these are all ductless. There's no ductwork connection. So the connection to these units is going to be a refrigeration connection. So a refrigerant line set is going to connect to these, and you're also going to dispose of condensate, because as we cool a airstream during the summertime, we're also going to dehumidify that air. Here you have a couple different options. The high wall option number 2 is typically what we see the most of, because it's pretty versatile. You can put in a good deal of locations, but there are other ducted options out there, or ductless options out there, I'm sorry. You have recessed cassettes. So number 3 is a recessed unit, so that's up into the ceiling. So it's a little bit more streamlined, a little bit more flush, a little bit more aesthetically pleasing, and those come in different sort of configurations, whether they're 4-way or 3-way, so they can throw air in different directions. And then number 1, we are starting to see more of in colder climates, especially during heating dominated climates, is a low wall unit or floor mounted units. And these, work or kind of mimic your traditional convectors. So if you're used to homes that have radiators in them, whether they're steam or hydronic, it's kind of, following the same principle. Cold air is going to sink down, that's where the return is, and then it's going to distribute the warm air at the top of the unit. So you get this sort of convective loop that takes place. And those are available as well. So you have a good deal of options when it comes to your design. And then we also have ducted units. So in certain situations, especially in passive house projects where the loads are so low, putting a recessed unit or a ductless unit, high wall unit in a bedroom that has a very low load may not be the most efficient thing to do, just because you may not find equipment that is as low enough, in terms of its BTU output. So you may start to see some short cycling take place. So in those situations, we typically advocate for using compact ducted units, which again are kind of recessed in the ceiling, and then we have ductwork that connects to 2 or 3 bedrooms. So we're conditioning those spaces locally, but we're doing it and we're kind of combining the loads together. So we're getting enough that we can really make sure that we have a good equipment selection to meet our load. Or you can go sort of the route that we see with with geothermal systems, where you go ahead and install a fully ducted system with distribution. So again, the same principles would apply of making sure the ductwork is sized correctly. And here you'll have something called an air handler that would be utilized. So it has a fan and a coil, and that will be connected to the outdoor unit. But you have some options. Now, when it comes to different types on the air source side, so we talked a little bit about the ducting or the terminal units, the indoor units, but we do have a couple different classifications or categorizations of these system types. So the smallest ones and the ones that you may see a lot of are mini splits. So they're typically a 1-to-1 configuration. So we have one outdoor unit connected to one indoor unit. And again, there's a refrigerant line set that makes that connection. And the indoor unit can be, again, it could be a floor mounted unit like this. It could be a high wall unit. It could be a recessed cassette. You have, options there. But these are typically smaller, tonnaged units. So these are typically designed to condition, a smaller space, and, are designed for that sort of 1-to-1, sort of configuration there. Now, if you wanted to sort of maximize the amount of heat you can deliver to different spaces with one outdoor unit, then we would move up to a multi-split. Right, so here we have one outdoor unit, but we have a few different indoor units. So we can connect this outdoor unit to typically up to 5 indoor units. And those can be located in different rooms or different parts of the home, and they would all receive their own refrigerant line set. So the refrigerant would kind of branch out from the outdoor unit, and say if you had 5 indoor units, you would have 10 different refrigerant lines, suction and liquid line for each one of those units going to the indoor. So you'd have to route those refrigerant lines through the building or through the home and make those connections. So there, some of the considerations, is again making sure that the refrigerant piping is done correctly. So there you would work with a good contractor that would follow the best practices and making those fittings and making those connections, as well as protecting the line set on the outdoors, right? Because we want to make sure that it's insulated. We want to make sure that insulation is protected from ultraviolet rays from the sun, so it has some sort of UV coating on it or barrier that's going to prevent that insulation from falling apart, through to UV radiation. And we want to make sure that, we're paying attention to the detailing of that penetration, right? So this is going to be one of the things that's going to be on your air sealing list is how am I going to insulate and air seal around, these refrigerant lines. So we want to make sure we're making good connections there to maintain the continuity of our air barrier. Again, these are a little bit larger, so these are typically 1.5 to 4 tons to 5 tons. So you're getting much more heat output on these units. And again, you can put them into different rooms, and they can be different types. Like you can see here, the second floor unit is a high wall, whereas the first floor unit is a low wall, right? So we have the ability to mix and match indoor units, and manufacturers have great sort of matrices that kind of show this, what you can do with different types. And then, as we alluded to earlier, the last kind of air source based product here is going to be your traditional kind of central split, right? Here, these are typically larger because we're dealing with a good deal of internal load. So these are going to be 2 to 5 tons. Again, you're going to have an air handler that's going to kind of take the place of a traditional furnace, and then all the good sort of ductwork connections need to be made up as well, and everything we talked about on the geo side. But these again are fully ducted. So we have one outdoor unit that is connecting with a refrigeration line set to the indoor air handler, and then that is providing both heating and cooling and dehumidification as well. So those are kind of the options that we have that are available to us, and then the idea is to really look at your design and try to find the product that's going to be the most suitable and sized correctly. That's always going to be the key, is making sure that the unit is the appropriate size for the project, and the terminal units are the appropriate size for the rooms that they're trying to condition, right? We want to make sure we have good matching there. So we've gone through about half of the slide deck, so I want to take a quick break here just to see if there's any questions about anything that we covered about the different types of equipment and the configurations that we commonly see.
Yeah, Adam, there's a couple questions here. Does existing ductwork or for forced hot air furnace need to be modified in any way for air source heat pumps, or can they be used as is?
You may have to modify it. So we'd have to look at a couple different factors. So this is where you would work with a contractor to see, right? So the ductwork, you know, that was the existing ductwork was sized for the airflow that the old unit was able to produce at the external static pressure that the old unit was able to produce. So, you know, when you're looking at installing a new unit, we need to make sure that, you know, one, the airflow is the same and the amount of pressure the fan can generate is the same. So in most cases, you're probably going to have to make, you know, some modifications to the ductwork to make sure that, you know, you have good delivery, right? Because that's always the shortcomings of a lot of different, you know, centrally ducted units is that, you know, and when you get towards the end of the lines, the velocity kind of, you know, peters out a little bit, and you don't have the same amount of delivery as you did when you were closer to the unit. So that's going to be important to take a look at. And then as well is on the return side, right? So you need to bring air back from the home so it can be conditioned. And sometimes, in my experience, you know, that return side of the system is kind of lacking. There's not enough return, or you know, and it makes it harder for that fan to really move the air. So I would say it's a case-by-case basis, but you'd have to, you know, investigate a bit.
Yeah, there another one here. Good one. Can heat pumps be utilized to operate hydro like radiant floor systems?
So there are air to water products out there, and that's a great segue to what we're gonna cover next. And you know, the thing we have to pay attention to with the air to water products is making sure that you're designing a low temperature distribution system. You know, when you look at, you know, traditional hydronics, you know, it's usually based around 180 degree delivery, 180 degree water going out to a baseboard or a radiator or some sort of, you know, of heating terminal unit. And that is going to be very difficult for a heat pump to produce, especially when it gets very, very cold outside. So, you know, when you're looking at this, and again, there are options out there, you do want to make sure that you're designing a low temperature distribution system, something that can completely heat the home at, you know, 110 degree delivered water. So it's more like looking at high mass style terminal units. So, you know, panel radiators, things that have a lot of thermal mass to them, they can deliver heat at low temperatures. But that is something that is available. It just takes a little bit more engineering.
All right, and then I think last one before we move on, there are a couple that we can save for the end. And I don't know how much you want to get into costs, but there are a few questions about costs related to, say, ductless versus ducted units, and like one-to-one mini split units versus like multi-split units, and how costs compare in those situations.
Yeah, I mean, you know, and costs are going to vary, you know, all over. I mean, I'm in the New York City market, so our costs are probably going to be higher than your market. But the high-level things I can say about, you know, costs is that, you know, obviously, you know, ductless units are going to be cheaper than ducted units, just because if you have to fabricate ductwork and install that ductwork, there's obviously a larger cost to be able to do that when you're looking at a new project. And then when it comes to, you know, one-to-one units versus, you know, multi-split units, obviously the multi-splits are going to be more costly. Again, there's more equipment, there's more labor, there's more refrigerant routing, there's more attention that needs to be paid to the joints that are being put together, so there's more potential to fail in some situations. So, you know, obviously there's going to be a little bit higher cost with those one-to-many types of systems. But the costs have come down from what we've seen, and you know, obviously as contractors are, you know, more educated and start to adopt and start to, you know, wrap their head around these products, you know, their costs will come down as well. We've seen that in certain markets, that, you know, some folks are, you know, really embracing this type of technology and are able to do it at a lower rate than 10 years ago when everyone was scared of these units. Cool. Alrighty, so let's, as I mentioned before, it was a great segue to kind of talk about, water heating. So now that we've kind of, talked about space conditioning, the options for heating and cooling, our air, let's talk about another, sort of load in our buildings. That's going to be water heating. So just like we discussed with a building, right, with a home, the first thing is going to be to really improve efficiency before we start to size and start to select our equipment. The same thing goes for water heating. So the first step is really to make sure that we're designing and we're selecting fixtures that are low flow, that are engineered, that have lower flow rates, right? Because that's going to put a less of a burden on our water heating devices to be able to produce that delivered water there. So we have a couple of recommendations for flow rates. We're looking at bathroom sinks, a gallon per minute, 1.5 GPM at showers and kitchens, and we start to see there are fixtures out there, and we start to see some complaints when you get down to 0.5 gallon per minute in residences. So like, 0.5 GPM for bathroom sinks. That's where there's not really enough flow there for folks to feel really satisfied. And that's where you start to get, the complaints. So we kind of keep it to 1 and 1.5 as the minimum there. And the last thing I'll say about this is that, the fixtures that are out there now that are engineered, that are designed to be low flow, are much better than the fixtures that were out there 10 years ago, right? So again, just like older heat pumps, older low flows, were not, they didn't have the great performance. There was always issues with pressure and all of that. But the new ones now have been, much better engineered and do provide a good amount of velocity and flow while keeping the flows, adequate. So that's going to be the first step, right? Make sure that we have, good fixtures, and then also make sure that we're insulating, those pipes that are delivering hot water to the space, right? Because we want to make sure that we're retaining as much heat as possible. So when it comes to system types, obviously we have some options, right? So one of the sort of tried and true options that have been around for a very long time, and you see this in areas of the country that have a high percentage of delivered fuels. So homes that use propane or oil to heat their homes, they typically have an electric resistive tank type water heater in the basement next to that furnace. So these have been around for a very long time. They're relatively affordable. So there's a low first cost, they're readily available. Contractors, there's less resistance there because, they're familiar and they're comfortable with these types of systems. What's happened from the manufacturing side is that they become a lot more efficient, right? So there's not much you can do with the water heating elements, right? So the resistive element that's in there, you'll see there's one at the top, one at the bottom. As you pass electricity through that resistive element, it generates heat, and that's what heats the water, right? Those, you really can't improve upon, right? So, those resistive elements are 100% efficient. So all the electric that goes into them, is, heat is being provided out. All the heat is being provided out. So they're essentially 100% efficient. So there's not a lot of room there to improve efficiency from the heat generation side. So what manufacturers have done is they've improved efficiency by looking at reducing standby losses, right? So these are much better insulated than the water heaters of old, and they are much more efficient at retaining heat. So there's less of a load on these systems as they're sitting there idle, waiting for someone to take a shower or to use hot water. So one of the things you can do if your flows are low enough is that you may not, want to have a tank of water sitting there in the basement, sitting on standby, throughout the middle of the day. And you may want to use a sort of point of use or a on-demand, typelet or tankless type. And those are out there and available as well. So these are tankless. So basically, same type of resistive element in here, but instead of running that element or those a pair of elements to heat a volume of water, 80 gallons, 70 gallons, here we're heating the water as the water passes through at the flow rate that the building is asking for. So these are kind of pass-through type units. So what you gain out of this is that there's no standby losses, right? Because the unit's not heating unless water flow is there. So there's we have standby losses are pretty much eliminated. It's pretty much 100% efficient there. Now, the only issue with these and things you have to pay attention to is that the process of taking water let's say at 50 degrees, right? And we want to raise the temperature of that water to 120 degrees because that's what we're accustomed to when we send water out to the building. So right there, we're talking a 70-degree increase, right? And to increase water by 70 degrees at 1.5 or 2 or 3 gallons per minute requires a lot of energy. Right, we need a lot of heat to be able to do that because we have to, raise the water 70 degrees, at that flow rate. So, as consequence of this is that the electric load on these units is fairly high. So the current draw is high. So if you look at, the nameplate data for, let's say, one of these units, and if we're sending a gallon per minute, 1 GPM through the unit, it's going to need to be 9 kW. So it's going to utilize 9 kilowatts of electricity at 40 amps. So that's, not terrible, right? That can work. But if you increase that, and let's say you need to go up to 4 GPM, if everyone's calling, everyone's asking for water, then that's going to use 35 kilowatts and 150 amps. And if you look at most residential electric services, it's typically 150 or 200 amps, right? So a lot of your available, electric is going to be eaten up by these units, and they're going to utilize a lot of current. They're going to be pulling a lot of current to make this happen. So that's one of the drawbacks to these is that you have to make sure you're accounting for the energy that these units are going to need to run. Now, improving upon this, and these have been around for a long time. These have been in the market. You see a lot of tankless in commercial buildings, but they are starting to make their way into the residential market. What we're seeing now that's a little bit newer is going to be heat pump based water heaters, right? So now, we want to do the same thing. We want to take advantage of that refrigeration effect, and we want to put in a unit that utilizes the vapor compression cycle that can produce more heat than energy that it consumes. So there's a couple different types when it comes to these heat pump water heaters. The first type is the one you see here. This is called an integrated heat pump water heater. And meaning that it's integrated is that it's all in one package, right? It looks like a conventional water heater that we're used to. So you have a tank at the bottom there that holds a volume of water, call it 50 gallons, 60 gallons, whatever it is. At the top of that tank, that's where the refrigeration device is located. So there we have the compressor, we have an evaporator coil. So here, what these units are doing is they're drawing air in from the building, from the home. They're absorbing heat from that air, and then they're injecting that heat into the tank, right? And it's going to go through the compressor, so we're going to be able to heat that tank up. A couple of things to pay attention to with these is that this unit, by nature, is going to cool the indoor air. Right, so that's something that we have to pay attention to is where do we site these units? How do we take advantage of maybe internal heat gains that we're going to have to try to utilize these? But they are going to if they're installed in the home, they are going to provide that cooling effect. They are going to reduce the temperature of the air, and that may not be a bad thing, but in certain situations it may lead to comfort problems or put an additional load on your space conditioning devices. You can, so another thing is, talking about that is that we also have to have enough airflow for these units to operate correctly. So a lot of times, you try to hide mechanicals, right? Because they're not the most aesthetically pleasing devices in our homes. So usually they're put into a mechanical closet somewhere and they're kind of tucked away. And that mechanical closet, because it's going to be the source of the heat for this particular integrated water heater, it's going to need to be big enough in order for us to harvest heat from that space. So if we don't have at least, it's typically like 800 cubic feet of air for most units available in that space that it can draw from, this unit is not going to work efficiently, right? That space is going to get very cold. The unit is going to go off on error, or it's going to fall back to its secondary heat source, which is electric resistive. So your overall efficiency is going to drop. So we need to make sure that we're accounting for the air that this unit's going to need in order to work correctly. And then some of these units can be ducted, so you can pull air from different areas and then exhaust that air in other places. So there are some accessory kits and things that you can do to make them a little bit more applicable for your particular project. The second thing we'll talk about with these is noise, right? So because there is a compressor and there are fans, integrated in this water heater, they're going to generate noise, and it's not, a terrible noise. It's about 55 decibels in most units, so it's louder than a refrigerator, but not as loud as a vacuum. So in certain instances, in the evening hours when this unit is running, that noise coming from the mechanical closet or coming from the area that's adjacent to where you are, it may produce enough noise that you generate some complaints. Right, so putting this unit in a proper space is going to be important as well, because it will generate some noise. And the last thing is it also will generate condensate, right? So as you condition the air and you remove heat, you're going to dehumidify that air a little bit as well. So we're going to have a plan to manage that condensate, whether it's a condensate pump that's going to pump the water somewhere, or if it's going to go into a drain. But that's something that's part of the installation, idea. When we have to start planning for the installation, that's what we're going to have to deal with. And there's some maintenance, right? These units, because you're bringing air in, there are filters that have to be cleaned as well, because we're trying to protect the coils from any dust or debris in the air. So there is a little bit of maintenance that is required as well. So that's one type, right? The second type is a split heat pump water heater. So these have been gaining in popularity and have been out in the market for a while now. And these, what they do is they put the heat pump portion of the unit outdoors and the tank stays inside. So the noise, the airflow requirements, all the condensate management, all of those things that were, an issue with the integrated heat pump water heaters are not an issue here, because this unit is outdoors. So these are a little bit different than the integrated heat pump water heaters. They use a different refrigerant. Most of the heat pump water heaters that are integrated use 134A as the refrigerant. These use carbon dioxide as the refrigerant. So these are able to produce very, very hot water and send it into the tank there. And what's interesting about these as well is that the entire refrigeration device is outdoors, and the connections you make to this device are water connections. So we're not sending refrigerant inside; we're just sending hot water inside. So these, are truly a sort of a unitary design, and then we're making water connections to the indoor unit. Same thing that we'd have to pay attention to with our space conditioning heat pumps. We need a good airflow around these units. We need to make sure they're elevated, so we're not getting them buried in snow, because they're going to be running year round. We want to make sure that if they're next to other units, there's enough airflow for each one of them. So there's a couple of things that a good contractor would pay attention to make sure that these are installed correctly. But these again are becoming more and more popular, and we're seeing a lot more of these go in multiple applications, not just single family. We're seeing them also in multi-family applications as well. And then just to round out all the other devices before we open it up for Q&A, there are other appliances as well that we have to look at. So cooking becomes, now what do we do with that? Again, you have familiar options. Electric resistive has been around for a while, relatively inexpensive. It's easy for folks to install these. And then you're starting to see a more improvement on that with induction, right? So induction cooktops are gaining in popularity as well. A little bit higher, electrical requirements than could be in certain situations than electric resistive. Special cookware you have to use, right? Because you're generating a magnetic field, so you need cookware that's going to be magnetic, so it can oppose that field and heat up, but much more efficient in terms of the cooking process, right? A lot of heat is lost to the surrounding air when you use an electric resistive cooktop like this, because you're heating the air as well as that pot of water. Whereas with induction, you're heating the pot of water. Right? The pot of water is what's heating the water in there. So it's a much more efficient process. Clothes dryers, another one where we have to pay attention to. So here again, you have electric, familiar, inexpensive, low, resistance from contractors to install these. And then you have heat pump clothes dryers as well. So these, utilize, again, a vapor compression cycle. They absorb heat on one side, they then reject that heat on the other, and they kind of, go through and heat those clothes and dry them out at the same time as that cool, damp air comes across the evaporator coil. The water is going to condense out of it. That's going to remove the moisture from the clothing. And then, hot air, dry air is going to be sent into the drum again to remove more of that moisture. So it's this, process of, providing heat and then wringing it out, and then providing heat, wringing out the air to get the clothes dry. Again, a little bit more expensive, obviously, than your electric-based systems. But again, we're starting to see more and more manufacturers come on board. So costs temperatures, should come down, and these should become a little bit more commonplace. And then the last thing is just additional considerations. So one of the things that you have to pay attention to when you're designing the electrical capacity for the home is that now you're going to be utilizing more electricity than a standard home, right? And that's not a bad thing. That's the whole point, right? We're trying to electrify buildings. So all of the loads that were typically, handled by the fossil fuels now are going to be handled by the electric-based devices. So we just need to make sure that we have enough capacity to handle all those additional devices, right? So heat pumps, we need to have, a 240 volt to 30 amp circuit for those. Induction range is same sort of thing, 40 amps. Heat pump dryer. So you kind of get, the equivalent. And this is not, across every single one, but this is kind of the average. So these are the loads we're going to add a little bit to our existing electrical load. So this needs to be sort of a conversation with an electrician just to make sure that they understand and there's enough capacity to handle all the other components, all the other fixtures and and lighting that you have in the building, right? And again, it should be more than enough, but it's a conversation worth having. And then the last thing is obviously, there is a, direct benefit from installing photovoltaics. The more energy that we can harvest and use inside the home, the better. So it's moving towards all electric devices now allows us to really utilize all the electricity that's being generated by an array on the roof. So it's a great pairing. So that's something that also should be, part of the initial conversation is, how do I utilize PV to offset, a lot of my electrical load and how can I make that effective? So there's this great sort of synergy between moving towards electric-based devices and adding renewables. So with that, we have about 9 minutes or so left. I will open it up for any additional questions that we didn't get to or questions that you just thought of as we went through that last section there.
Yeah, there's a couple of good questions in here, Adam. Do you recommend any type of specific piping for like hot water, heat pump hot water heaters to ensure maximum efficiency of those units?
Yeah, so there is, a process of really making sure and sort of scrutinizing the design there. So, there's a bunch of research and there's a bunch of folks in the field that have done a lot of research on this. And, the idea is to really make sure that the pipe sizes are correct and they're branching down, effectively, right? So if we can reduce the amount of water in the distribution piping, we can reduce the amount of off-cycle losses we have from that water sitting there and losing heat to the space. So it's really, working with an engineer or a plumber to kind of scrutinize those pipe sizes and say, okay, well, do we really need 3/4 or can we scale down to 1/2 inch? Especially if we're putting low flow fixtures in, if we can reduce the overall volume of water sitting in our distribution system, there's some efficiencies to be gained there.
Yeah, and then there are a couple more questions just about like the air to water. Maybe you just elaborate on when applicable usage for air to water heat pumps might make sense for people to consider, and if so, what types of things should they keep in mind that might be different from conventional air source.
When it comes to space heating?
Yes, yeah.
Yeah. So I think, the one thing you have to pay attention to with this is that, again, so one of the things, again, we're not going to be able to generate very, very high temperatures. So we're going to want to make sure we're using, terminal units that are high mass. So that's either, flat panel radiators or, in-floor heating, radiant heating, things that we can utilize lower temperature water to provide, a good amount of heat. Again, is scrutinizing the design of the home, making sure it's as efficient as possible. The other thing you have to pay attention to, though, with this is space cooling. Right, so those typical terminal units that we have, let's say flat panel radiator, during the summertime, we can't turn that into a cooling device, right? Because we would have issues. Not to say you can't do it; it's just that you wouldn't want to do it. You'd have to really make sure that you're controlling humidity very, very well, or you're going to have that radiator becoming soaking wet as it cools off the air. So there's going to have to be some sort of thought about how we're going to cool the building, cool the home. So that may just be a water coil in an air handler. So you can put a hydronic coil in an air handler, so then during the cooling season you would divert the water flow to the coil, and then there would be a ductwork system that would deliver the cooling to the space, and then that coil that's inside the air handler would then dehumidify the air, and you could get rid of the condensate that way locally at that air handler. But that is the big thing, is that when we look at the cooling side, what do we have to figure out a solution there.
Yeah, thanks. Are there efficiency differences for ductless units between like 1-to-1 and the multi-split units?
Yeah, I mean, typically the 1-to-1 units are more efficient than the multi-splits. It's just because it's a much better pairing in terms of sizing, because you have instances where the outdoor unit on a multi-split is on and it's running, right? But it's only running for maybe 1 or 2 indoor units, right? So there's and it can vary itself down. It can lower the compressor speeds, but there's going to be a minimum, right? There's always a minimum. We can't indefinitely lower the speed all the way down to a fractional percentage. There's going to be a basement there that we can't go past. So there may be instances where the outdoor unit is oversized for the indoor units that are calling, and that may pose an issue from efficiency. So typically the 1-to-1 units are more efficient than the 1-to-many.
I have kind of a big picture question here, and I'll let you take a stab at it, and then I can actually provide some commentary as well. But what is government, whether that be at the national level or local, state level, or even municipal level, doing to encourage or even require this type of technology in new construction moving forward?
Yeah, I mean, obviously it depends on where you are. There's different, areas that have legislation that's been either developed, that has been submitted, that has been passed, calling for, construction of new buildings to go all electric. The other side of it is also there are areas that, are working towards, cleaning up the electric grid, as well as, infusing more renewables into the picture. So, carbon has become the metric in a lot of areas, looking at carbon reduction. Here where I am in New York City, we have Local Law 97 that looks at the carbon emissions from buildings and sets a cap, and then associated fines. So that's really driving the industry to come up with solutions. But it's kind of 2 things have to happen. We need to now have clean electricity to be able to tap into, and then efficient devices that are there. And it's got to make economic sense as well. So I think some utilities are looking at different rates for heat pumps. That's been tossed around in some places. Is there a different rate classification for heat pump versus standard electric rate to try to make it more cost effective there? And there's some benefits from a utility perspective in terms of load balancing. Throughout the year, they are able to take advantage of their assets during the winter time and use them. So I mean, there's conversations happening, and I think as more and more areas really make this happen, and there's more case studies and success stories out there, then I think you'll start to see more folks get behind that, and you'll see more requirements.
Yeah, and I can say with ICF having worked in both Massachusetts and Connecticut, that both those states are working on legislation and codes at the state level that would both encourage and in some cases require the use of high performance all electric equipment. Massachusetts is in the process of working on a stretch code for 2023 that would really highly encourage the use. And then in Connecticut, I believe they are in the process of passing a code that would actually require buildings to be fossil fuel free within a number of years. That's still in progress, but certainly something to keep an eye out for. So a lot going on to be aware of.
Yeah, and the last thing I would just say is that it's a great synergy with passive house, right? So if you're building a passive house, it just makes a lot of sense to go with refrigerant-based systems. They pair very, very well. The efficiencies are there. All of the issues that you sometimes have with trying to implement a heat pump in a conventional non-passive house home are typically not an issue. So it's a very, very good pairing.
There's a question, where would folks go if they wanted to find contractors or builders that, are either certified or have knowledge in some of these passive house fundamentals and methods?
Yeah. I mean, I would look at, there's relevant organizations. I know, FIAS and Passive House Institute have, trades people, tradesperson certification. So there are some areas there where you can go in and look to see if as a contractor, certified there, do they understand passive house principles? And then I would also look at manufacturers, right? So the manufacturers of the equipment that you're looking to utilize, a lot of times they require contractors to go through training and go through a certification process in order for them to really make sure they understand how to install these systems, right? Because again, it behooves them to make sure that their contractors are trained. It'll save on warranty claims and things like that. So I would check the manufacturer's, certification process as well on their website to find local contractors.
Yeah, thanks, Adam. And that brings us right to 1 o'clock. So Anna, I'll pass it to you just to wrap things up with the recording of the webinar and where folks can get CEUs for today's presentation.
Yeah. Yep. So just a reminder, we will be posting the recording of this presentation on the Connecticut Passive House website, and I will be sending out a link when that is ready to be shared to all of you who have attended today. And also we will be sending out a couple of surveys. One survey will be asking for your feedback on this presentation, and then another survey will be specifically for anyone who wants to obtain AIA CEU credits. So stay tuned for those 2 emails going out.
Yeah, thanks, Anna. And just a reminder again, today's presentation was brought to you by the sponsors of Energize Connecticut and is part of an ongoing series. So keep an eye out for invitations to future events. So with that, yeah, thanks, Adam. Thanks, Anna. Have a great afternoon.
Yeah, take care, everyone. Thanks for joining.
Bye. Bye.